Welcome. Take a moment to settle in, without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered, or understood, or followed to the end. You can fall asleep at any point, and you will not miss a thing. Tonight we are going to talk about satellites, slowly, without hurrying. There is a drawing in Newton's Principia that explains an orbit better than any equation. A cannon sits on top of an impossibly tall mountain above the air and fires horizontally. The first ball arcs out and lands. The second, fired harder, lands further away. The third travels so far that the ground beneath it has curved away by the time it falls, and it lands further still. And then there is a speed at which the ball falls exactly as fast as the ground curves out from under it, and it never lands at all. It goes all the way around and arrives back at the cannon from behind. An orbit is a fall that keeps missing the ground. That is an orbit, and the drawing is honest about what it is. A satellite is not held up by anything. Nothing suspends it, nothing pushes it, no force cancels its weight. It is falling, continuously, and it has been falling for as long as it has been up there. The only difference between the satellite and a dropped stone is sideways speed. The stone has none, so it falls to the ground beneath it. The satellite has enough that the ground it would have hit is no longer there. The speed required is specific and it is large. Near the ground, in the lowest orbits anything uses, it comes to about 8 kilometers every second. Written as a car speedometer would put it, that is 28,000 kilometers an hour. At that rate, a satellite crosses the width of a country between 2 sentences of this narration, and it laps the entire planet in roughly 90 minutes. There is no coasting to it, and no gentle version. Below that speed, whatever is up there comes down. It laps the whole planet in 90 minutes. The number comes from the curve of the Earth itself, and it can be recovered with arithmetic that needs no telescope. Over a horizontal distance of about 8 kilometers, the surface of the planet drops away by roughly 5 meters. Anything falling freely near the ground also drops about 5 meters in its first second. So a body moving sideways at 8 kilometers per second falls 5 meters in that second and finds the ground has fallen 5 meters too. The two cancel. That is the whole of it. The arithmetic also explains why the speed is not a single number but a sliding one. Higher up, the pull of the Earth is weaker and the curve of the horizon is gentler, so less sideways speed is needed to keep missing the ground. A satellite 400 kilometers up must move at about 7.7 kilometers a second. One at 20,000 kilometers needs less than half of that. The relationship is fixed, it was worked out before anything flew, and it is the reason an engineer can choose an altitude and know the speed that comes with it without any choice in the matter. This is why the shape of the drawing matters more than the mathematics. Generations were taught that satellites are held in place, as though orbit were a shelf, and the language survives in the way we speak about them even now. We say a spacecraft is placed in orbit, or parked, or stationed. Every one of those words suggests rest. What is actually happening is the least restful thing available. A permanent, unbroken fall at 8 kilometers a second, sustained for decades. One consequence of the trade deserves stating early, because it governs everything in the later chapters. Going up is cheap compared with going sideways. Reaching a height of 400 kilometers, on its own, takes a fraction of the energy required to then be traveling fast enough to stay there. A rocket that rose vertically to that altitude and stopped would fall straight back down within minutes. Almost all of the fuel burned on a launch is spent not on climbing, but on turning, gradually, until the vehicle is moving horizontally at 8 kilometers a second. The altitude is the easy part, and it is not what anyone is paying for. Nothing holds it up, and nothing ever has. The confusion carries into what people believe about weightlessness. It is widely assumed that astronauts float because they have escaped gravity, that they have climbed above its reach. They have not. At the altitude of a large crewed station, some 400 kilometers up, the pull of the Earth is about 90% of what it is at sea level. If a tower could be built to that height and someone stood on top of it, they would weigh very nearly what they weigh at home. They have not escaped gravity, they are inside it. The fall is not quite uniform across a large structure, and the difference has a name. A station 200 meters from end to end has one end slightly closer to the Earth than the other, and the closer end is pulled a fraction harder. The result is a very gentle stretching along the line, pointing down, weak enough that no one aboard notices it directly, strong enough that a station left alone will slowly rotate until its long axis points at the planet and then stay there. Engineers call this the gravity gradient, and some spacecraft are stabilized by nothing else. What is missing aboard a satellite is not gravity, but the floor. On the ground, the sensation of weight comes from the ground pushing up against the soles of the feet, a compression that travels through the skeleton and is read as heaviness. In freefall, there is nothing pushing back, because the floor is falling at exactly the rate the body is. The station falls, the walls fall, the water in a cup falls, the astronaut falls, and everything falls together at the same rate, so nothing presses against anything else. Nor is the fall entirely free, close to the Earth. The atmosphere does not stop at a line. It thins outward, and a trace of it persists at 400 kilometers, enough to drag against anything passing through at 8 kilometers a second. A large crewed station loses altitude continuously because of it, on the order of 100 meters a day, and must be pushed back up several times a year by an engine firing along its direction of travel. Left alone, without those pushes, it would come down within a couple of years. The correct name for it is freefall, and some agencies now insist on the term microgravity to avoid the word weightless entirely. The distinction is not academic. Understanding that an orbit is a fall explains, in one stroke, why a spacecraft cannot simply stop and hover above a chosen city, why the crew cannot open a window, and why every object aboard, from a spanner to a droplet of water, behaves as though it has been released rather than placed. The floor is falling at exactly the same rate as the body. There is a further consequence that is rarely stated plainly. Because the motion is a fall, it cannot be paused. A satellite has no brakes and no idle. Slowing it down does not make it hover lower, it makes it descend, and descending makes it faster, and faster makes it heat, and heat is how orbits end. Every satellite in the sky is therefore in the same condition, moving fast enough to keep missing the planet and unable to do anything else without ceasing to be a satellite at all. It is worth sitting with the strangeness of this for a moment because it is the foundation of everything that follows in this video. The most stable structures human beings have ever built above their heads are not resting on anything. They are held by nothing, supported by nothing, and their permanence is the permanence of a stone thrown so hard it never comes back down. Every communications relay, every weather image, every navigation signal arriving in a pocket depends on that single arrangement. The most stable thing above us rests on nothing at all. Newton never saw one, of course. He worked out the cannonball nearly 3 centuries before anything was launched, and he presented it as a thought experiment rather than a proposal. It required a mountain above the atmosphere, which does not exist, and a cannon of impossible power. What he was demonstrating was not engineering but continuity, that the same law which brings a ball down also, at sufficient speed, carries it around. The machines came later. The idea was complete from the start. There is one more thing the cannonball drawing gets right, and it took a long time to be believed. The curve the ball follows when it does come back around is not a circle but an ellipse, with the center of the Earth at one focus rather than at the middle. A circular orbit is the special case where the ellipse happens to be perfectly round, and it is rare in practice. Almost everything in the sky above us is traveling a slightly lopsided loop, moving a little faster when it is low and a little slower when it is high, exactly as a thrown stone speeds up on the way down. The idea was finished 270 years before the machine. If you find this useful for sleeping, a like helps other people who are awake at this hour find it too. Subscribing means the next one arrives without you having to look for it. That is all I will ask tonight. For about 2,000 years, educated opinion held that the sky obeyed different laws from the ground. Down here, things were held to move in straight lines, to slow, to fall, to decay, and to change. Up there, motion was circular, unending and unchanging, and the material was thought to be a fifth element entirely unlike earth, water, air, or fire. This was not superstition dressed up as science. It was a reasonable reading of the evidence available to anyone who looked, because nothing in the sky had ever been seen to fall, and nothing on the ground had ever been seen to circle forever. For 2,000 years, the sky had its own physics. The division was tidy, and it was useful. It explained why the stars returned to the same places, why the planets kept their courses, and why the world beneath was so obviously different in character. It also made a certain kind of question unaskable. If earthly and heavenly motion were separate in kind, then asking what holds the moon up was like asking what color a sound is. The question had nowhere to land. What broke the division was a suggestion so simple it sounds like a joke, and it is usually told as one. The story of the apple is very likely true in outline, since Newton described it himself in old age to more than one visitor, though the detail of the fruit striking his head was added by others later. What he described was watching an apple fall in the garden at Woolsthorpe and wondering why it always fell straight down toward the center of the earth, and then wondering how far up that same tendency might reach. How far up does the pull of the earth still reach? The leap is not the apple. The leap is the second half of the thought, that the moon is doing the same thing as the apple, that the moon is not held in place by a sphere, nor carried by a celestial mechanism, but is falling toward the earth continuously and missing, exactly as a thrown stone would if thrown hard enough. One law, one behavior, from the fruit in the garden to the body in the sky. Nothing in the previous 2,000 years had proposed anything of the kind. It is one thing to suggest that, and another to test it, and the test is where the work lies. The Moon sits about 60 times further from the center of the Earth than the surface does. If the pull weakens with the square of the distance, as Newton suspected, then at the Moon it should be weaker by 60 times 60, which is 1 part in 3,600. A body near the ground falls a little under 5 meters in its first second. The Moon, therefore, ought to fall about 1 1/3 millimeters in the same second. That figure can be checked against the sky, because the fall of the Moon is visible as the amount by which its path bends away from a straight line. The length of the month was known precisely, the distance to the Moon was known reasonably well, and a little geometry gives the deflection directly. Newton did the comparison and found that the two numbers agreed, in his own careful phrase, pretty nearly. Not exactly, pretty nearly. The Moon falls 1.3 millimeters every second. It is worth being clear about how small that number is, because it is the reason nobody had noticed. 1.3 millimeters is roughly the thickness of a stack of a dozen sheets of paper. That is the entire distance by which the Moon deviates from a straight line in a second, and it is the whole of what holds it. Over an hour, the deflection amounts to a few meters. Over a month, it closes a circuit of 2.5 million kilometers, and at no point along the way would an observer standing on the Moon feel anything at all. The gap between pretty nearly and exactly is the reason the idea sat unpublished for the better part of 20 years. Part of the discrepancy came from the value he had used for the size of the Earth, which was not good enough, and a better measurement later closed most of it. But there was a second obstacle, mathematical rather than observational, and it was serious enough to stop him. The problem was this: an apple is a few meters from the surface of the Earth, and the Earth is not a point, but a vast ball of matter spread over thousands of kilometers. Some of that matter lies directly beneath the apple, some off to the side, some on the far side of the planet, and every piece of it pulls in a slightly different direction. To say the apple is 1 Earth radius from the center assumes the whole planet can be treated as though its mass sat at a single point in the middle. That is not obviously true, and if it is false, the entire comparison collapses. It is easy to forget how strange the inverse square law looked to people who first read it. It says that a body reaches out across empty space and pulls on another body it never touches, instantaneously, with no intervening mechanism of any kind. Newton was uncomfortable with this himself and said so in print, declining to offer a cause and insisting only that the description fitted the observations. Critics on the continent regarded the whole thing as a return to occult influences dressed in mathematics. The objection was not unreasonable. The answer to it did not arrive for another 200 years. Does a whole planet pull like a single point? Newton eventually proved that it does, for any sphere whose density depends only on depth, and the proof required the calculus he was inventing alongside it. A uniform shell of matter attracts an outside body exactly as though the entire shell were gathered at its center, and a solid ball is a stack of such shells. It is one of the most convenient results in physics, and it is not intuitive in the least. Without it, the sentence about 1 Earth radius would have had no meaning at all. The work reached print in 1687, and it did so largely because Edmund Halley asked the right question and then paid for the printing himself when the Royal Society could not. Halley had come to ask what curve a planet would follow under an attraction that weakens with the square of distance. Newton replied that it would be an ellipse, and that he had calculated it years earlier. Asked to produce the calculation, he could not find it, and had to reconstruct the whole argument. That reconstruction became the book. The Royal Society could not pay, so Halley did. What the book established is easy to state and was very hard to accept. There is one rule. It applies to the apple, to the moon, to the tides, to the flattening of the earth at its poles, to the slow wobble of the equinoxes, and to every satellite that would later be launched. The sky was not made of a different substance, obeying different laws. It was made of the same stuff falling in the same way, and the only reason it had looked otherwise was that nothing up there had ever run out of sideways speed. It is worth noticing what this cost in comfort. The old picture had the heavens as a place of permanence, immune to the decay of the world below, and that permanence had been consoling for a very long time. The new picture put the moon in the same condition as a falling stone. Everything above was subject to the same pull, the same arithmetic, and the same eventual end. Nothing was exempt. That is a colder sky, and it took a generation for it to become ordinary. One rule: from the fruit in the garden to the moon. There is a detail in the reasoning that deserves its own moment, because it is the part most often skipped. Newton did not merely assert that the pull weakens with the square of the distance. He showed that this particular weakening, and no other, produces the ellipses that Kepler had already extracted from decades of observation. A pull that weakened with distance alone, or with the cube of it, would have produced curves that do not match the sky. The inverse square is not a convenience. It is the only shape of law that fits what was already known. For the purposes of everything that follows, the practical consequence is the one that matters. Once the law is written down, an orbit stops being a mystery and becomes a calculation. Give the height, and the law returns. The speed, the period, the shape of the path, and the minute it will pass overhead. Every satellite ever flown was placed using arithmetic that was complete and correct 2.5 centuries before the first launch, and needed nothing but a rocket to become useful. After 1687, an orbit was arithmetic, not mystery. Before anyone spoke of orbits, the sky was understood as a piece of machinery. The planets were not thought to travel through empty space. They were carried, each one fixed to a transparent sphere that turned about the Earth, with the spheres nested one inside another, like the layers of an onion. The outermost carried the fixed stars. The system was worked out in detail, and in its fullest ancient version, it required 55 separate spheres turning at different rates to reproduce what could be seen. The planets were not traveling, they were carried. 2 commitments held the whole structure together, and both were about perfection rather than observation. The first was that the heavens do not change. Whatever exists above the moon was held to be permanent, incorruptible, exempt from the decay that governs everything below. The second was that celestial motion must be circular and uniform, because the circle was regarded as the perfect figure and the heavens could not move imperfectly. Those 2 commitments were not idle. They decided in advance what any observation was allowed to mean. When something new appeared in the sky, it could not be a change in the heavens, because the heavens do not change. So it had to be something in the air. Comets in particular were classified as weather. They were listed alongside rainbows and lightning as phenomena of the upper atmosphere, and for centuries that is where the textbooks kept them. A comet was filed under weather, not astronomy. The first crack came in 1572, when a star appeared in Cassiopeia that had not been there before, bright enough to be seen in daylight. The question of whether it lay above or below the moon could be settled by measurement, and Tycho Brahe settled it. If the object were near, in the atmosphere, then observers at different places on Earth would see it against slightly different backgrounds of stars. He measured, repeatedly, and with instruments better than anyone had built, and found no such shift at all. It is worth pausing on the instruments Tycho used, because everything that follows rests on them. He had no telescope. None existed. What he had were very large graduated arcs of brass and steel, some of them several meters across, mounted so rigidly that they did not flex, and read by eye with the help of a scale divided more finely than anyone had managed before. With those he measured positions to within about 1 minute of arc, roughly a 30th of the width of the full moon, and he did it night after night for 20 years. No shift meant the object was far away, out among the fixed stars, in the region that was not permitted to change. It faded over the following months and vanished, which made the conclusion worse rather than better. Something in the incorruptible heavens had appeared and then decayed. We now know it was a star exploding, but the identification was not the point. The point was that a commitment 2,000 years old had been broken by a measurement anybody with good instruments could repeat. Something in the unchanging heavens had changed. 5 years later, a bright comet gave Tycho a second opportunity, and this one did more damage. Applying the same test, he showed that the comet was well beyond the moon, which already contradicted the classification of comets as weather. But its path also carried it straight through the region where the crystalline spheres were supposed to be. Either the spheres did not exist, or they were not solid, or the comet went through them. None of the three was acceptable to the old picture. The commitment to circles lasted longer, and it was defended with real ingenuity. Planets do not in fact move at a steady pace against the stars. They slow, stop, and briefly reverse before resuming. To reproduce that with circles, astronomers had each planet ride on a small circle whose center traveled around a larger one. Where that was not enough, the larger circle was offset from the Earth, and a further point was introduced about which the motion was uniform, even though it was not uniform about anything else. Kepler's own reasons for pursuing the problem were not the ones the result is remembered for. He was searching for a harmony, a geometric pattern underlying the spacing of the planets, and had earlier proposed that their orbits were separated by nested regular solids, the cube, the tetrahedron, and the rest. He never abandoned that ambition, and he regarded the third law as evidence of exactly such a harmony, rather than as an engineering tool. The rule that places satellites was found by a man looking for music in the arrangement of the sky. This was not stupidity, and it deserves to be said clearly. The system predicted positions well enough to be used for navigation and calendars for well over a millennium. Its problem was not that it failed, but that it never finished. Each improvement in observation required another adjustment, and the adjustments never converged on anything simple. A structure that needs a new part every time you look more closely is telling you something, and it took a long time for anyone to hear it. It never failed outright, it simply never finished. What ended the circle was one planet and one number. Johannes Kepler inherited Tycho's observations, the most accurate ever taken without a telescope, and spent years fitting the motion of Mars. He found an arrangement of circles that reproduced the positions to within 8 minutes of arc, which is about a quarter of the width of the full moon, and was better than any predecessor had managed. By every standard of the previous 15 centuries, he was finished. He refused it. His reasoning was that Tycho's measurements were reliable to about 2 minutes of arc, so an error of 8 could not be blamed on the observer. It had to belong to the model. On the strength of that single discrepancy, smaller than the eye can resolve, he abandoned the circle entirely and began testing other curves. He later wrote that those 8 minutes alone had pointed the way to a reform of all astronomy. 8 minutes of arc, and he threw out the circle. The curve that fitted was the ellipse, published in 1609, with the sun not at the center, but at one of the two foci. Alongside it came a second rule about speed. A line drawn from the sun to the planet sweeps out equal areas in equal times, which is a compact way of saying the planet moves faster when it is closer and slower when it is further away. Between them, the two rules did away with every epicycle at once. The rule about equal areas is easy to state, and its meaning is easy to miss. It says that a planet sweeps out the same area in every equal interval, which forces it to travel quickly when it is near and slowly when it is far. What is being conserved is a quantity that would not be named for another 2 centuries, and Kepler had no idea he had found it. He was describing a regularity in the numbers. The reason for the regularity arrived much later and turned out to be one of the deepest rules in physics. A decade later, Kepler added the rule that matters most for anything launched from the ground. The square of the time a body takes to complete one circuit is proportional to the cube of its average distance. It is an odd-looking statement, and it is extraordinarily useful because it links 2 quantities that can each be measured independently. Give it a distance and it returns a period. Give it a period and it returns a distance. Nothing about the body itself enters into it. Give it a height and it returns the hour. It is worth being precise about what Kepler had and had not achieved. He had 3 rules that described the motion accurately and predicted it reliably, and he had no explanation for any of them. He suspected some influence radiating from the sun and pushing the planets along, which is not what happens. The rules were correct, and the mechanism was missing. And that gap remained open for the better part of a century, until it was closed by the argument described in the previous chapter. The reason all of this belongs in a video about satellites is that the third rule is still the working tool. An engineer choosing where to place a spacecraft does not begin with rockets or with metal. They begin by deciding how often it should come around, and the rule converts that decision straight into an altitude, or refuses it. Every orbit described in the chapters that follow was chosen inside a constraint written down 400 years ago by a man who was trying to understand Mars. The rule that places satellites was written for Mars. In January of 1610, Galileo turned a newly improved telescope toward Jupiter and saw 3 small points of light arranged in a line beside it. He assumed at first that they were faint stars that happened to lie in that direction. The following night he looked again, expecting Jupiter to have moved on against a fixed background, and found instead that the points had rearranged themselves. A few nights later, there were 4. They were not stars. They moved every night. He watched them for weeks, and the pattern resolved itself. The points swung from one side of the planet to the other, sometimes vanishing entirely for a night before reappearing on the far side. They were not scattered at random, they stayed close to Jupiter, and they kept to a line. The only arrangement that produces this is a set of bodies circling the planet, seen edge-on from a great distance. The consequence was immediate, and it was not primarily astronomical. The prevailing system held that everything in the sky turned about the Earth, and one of the strongest objections to any alternative was that a moving Earth would surely leave its own moon behind. Here were four bodies plainly circling something that was not the Earth, and plainly not being left behind by it. The objection did not survive the observation. Four bodies circling something that was not us. The word we now use for such things was coined for these four objects, and its origin is worth knowing. Johannes Kepler, writing about Galileo's discovery in 1611, reached for the Latin word for an attendant who accompanies an important person, a member of a retinue or a bodyguard. He called Jupiter's companions its satellites. The term sat almost unused for centuries, and was then taken up wholesale for the machines described in this video, which are therefore named after the entourage of a Roman official. The word means an attendant in a retinue. Galileo did not call them what we call them. He named the four moons after the ruling family of Florence, publishing them as the Medicean stars, and the dedication was not idle flattery, it secured him a court appointment and a salary. The names did not last. They were replaced by the mythological ones still used today, proposed by a rival who had observed the same objects at almost the same time, and whose claim to independent discovery was disputed for centuries afterward. Others followed as telescopes improved. Titan, the large moon of Saturn, was found by Christian Huygens in 1655, and four more Saturnian moons were added over the next 30 years by Giovanni Cassini. Each addition made the same point more firmly. Circling is what bodies in the sky do, and the Earth is not the thing they circle. By the end of that century, the question was no longer whether other worlds had moons, but how many, and how to predict where they would be. The most sustained practical use of those moons had nothing to do with astronomy. Finding longitude at sea requires knowing the time at a reference place and comparing it with local noon, and before accurate clocks existed, there was no way to carry a reference time aboard a ship. Jupiter's moons offered one. Their eclipses happen at the same instant for every observer, so a printed table of eclipse times is a clock visible from anywhere on the night side of the planet. The most useful discovery of the period came not from finding a new moon, but from timing an old one. Jupiter's innermost bright moon passes into the planet's shadow on every circuit, and the moment it disappears can be recorded to within a minute or two. Since the circuit is regular, those disappearances ought to arrive on a fixed schedule, and a table could be printed years in advance. When Ole Römer compared the printed times against the observed ones, they did not match. At sea, it never worked. Observing an eclipse requires a telescope held steady on a target the size of a pinhead, and the deck of a ship at night does not permit it. On land, it worked beautifully, and it was used for decades to fix the positions of cities. When the coastline of France was resurveyed by this method, the country turned out to be noticeably smaller than the existing maps claimed, which prompted the remark from the king that he had lost more territory to his astronomers than to any enemy. The eclipses arrived early, then late, then early again. The four moons also keep a pattern with each other that took a long time to explain. The inner three circle Jupiter in periods that stand in a precise ratio of 1 to 2 to 4, so that they return to the same alignment again and again rather than drifting into random arrangement. That locking is maintained by their own mutual pulls, and it is not a coincidence of the present day, but a stable arrangement that reasserts itself when disturbed. The same kind of locking is now known in many systems, and it was first seen here. The discrepancy was not random. When the Earth was on the same side of the Sun as Jupiter, the eclipses ran ahead of the table. When the Earth was on the opposite side, they ran behind, and the total swing between the two extremes came to about 22 minutes. Romer saw that the pattern followed the distance between the two planets rather than anything happening at Jupiter, and drew the conclusion in 1676. Light does not arrive instantly. It takes time to cross the extra distance. This was the first measurement of the speed of light, and it was obtained from a moon of another planet by an astronomer who had set out only to correct a timetable. The value he could extract was low by roughly a quarter, because the size of the Earth's orbit was not yet well known, and that number enters the calculation directly. The method was sound, and the arithmetic was sound, only the input was imprecise. Later measurements of the same eclipses, with a better figure for the orbit, closed the gap. The speed of light, found by correcting a timetable. The moons of Mars arrived much later, and they behave in a way that is directly relevant to everything that follows. Asaph Hall found them in 1877 after weeks of searching, and very nearly gave up before his wife persuaded him to continue for one more night. They are small, irregular lumps rather than spheres, and they orbit extremely close to the planet. The inner one is the interesting case. It circles Mars in about 7 hours and 39 minutes, which is considerably less than the time Mars takes to turn once on its axis. The consequence is visible from the surface. That moon overtakes the ground beneath it, so it rises in the west, crosses the sky, and sets in the east, twice in every Martian day. Everything else in the Martian sky goes the other way. It rises in the west because it outruns the ground. That single fact contains, in advance, the whole principle of the geostationary orbit described later in this video. Whether a satellite appears to move across the sky, hang still, or travel backwards depends entirely on how its period compares with the rotation of the body it circles. Faster than the ground and it overtakes, slower and the ground overtakes it, exactly equal and it hangs. Mars has been demonstrating the first case for as long as there has been anyone to watch. There is a second lesson in that inner moon, and it is about endings. Because it circles faster than the planet turns, the tides it raises on Mars pull backwards against it rather than forwards, and it is losing height. The rate is small, a couple of centimeters a year, but it is steady and it does not reverse. In some tens of millions of years it will come apart, and the pieces will either fall or spread into a ring. An orbit close to a large body is not a permanent address. An orbit close to a large body is not permanent. Taken together, the natural satellites established every principle that the artificial ones would later rely on, that bodies circle bodies, that the period follows from the distance, that the arrangement can be predicted years ahead and checked against the sky, that timing those predictions carefully enough turns a moon into an instrument, and that nothing in such an arrangement is permanent, only slow. All of it was known from watching, long before anything was built. Everything a satellite does begins with a single trade, and it is not negotiable. Height and speed are locked together. A spacecraft cannot be placed low and slow, or high and fast, because the arrangement that keeps it up is the balance between how hard the Earth pulls at that distance and how fast the ground curves away. Choose the height and the speed follows. Choose the speed and the height follows. There is no third option and no setting in between. Choose the height and the speed is already decided. The direction of the trade catches most people out. It seems natural that going higher should require going faster, since higher sounds like more effort, and getting there does indeed cost more fuel. But once arrived, a higher satellite travels more slowly than a lower one. The pull of the Earth is weaker up there, so less sideways speed is needed to keep missing the ground, and the orbit that results is more leisurely in every respect. The numbers make the pattern concrete. A satellite a few hundred kilometers up moves at something close to 8 kilometers a second and completes a circuit in roughly 90 minutes. Push it out to 20,000 kilometers and the speed falls below 4 kilometers a second, while the circuit stretches to about 12 hours. Go further still and the motion becomes slower and the circuit longer, without limit. 90 minutes down low, 12 hours further out. There is an upper end to the trade, and it has a name. As the chosen height increases, the required speed falls, but the speed needed to reach that height rises, and at a certain launch speed, the two curves meet. The object has enough energy to keep climbing without ever coming back. That threshold is about 11 kilometers a second from the surface, and it is called escape velocity. Below it, everything returns. Above it, nothing does. Every satellite ever launched sits deliberately below that line. The rule connecting the two was written down 400 years ago, and it has not needed amending. The square of the period is proportional to the cube of the average distance from the center of the Earth. Because the exponents differ, the relationship is not a straight line. Doubling the distance does not double the period, but multiplies it by nearly 3. The effect compounds quickly, which is why the range of useful orbits is so wide. Somewhere in that range there is a distance at which the period comes out to exactly 1 day, and that distance is the most valuable piece of real estate above the planet. It sits about 35,800 kilometers above the equator. A satellite placed there, moving in the same direction as the ground turns, takes exactly as long to go round as the Earth takes to spin. From below, it does not appear to move at all. One height, and one only, where it appears to hang. It is worth being exact about what is happening there, because the appearance is deceptive. The satellite is not stationary, and it is not hovering. It is traveling at about 3 kilometers a second, which is faster than any aircraft has flown, and it is falling continuously, like everything else. What makes it seem still is that the point on the ground beneath it is also moving, in the same direction, at a rate that keeps the two lined up. Stillness is a coincidence of two motions, not an absence of motion. There is one more property of the trade that has no equivalent on the ground and consistently confuses newcomers. To catch up with something ahead of you in the same orbit, you must slow down rather than speed up. Firing forward raises the orbit, and a higher orbit takes longer, so accelerating causes you to fall behind. Firing backward drops you into a lower, faster orbit which closes the gap, after which you climb back up to meet the target. Every docking in history has been carried out by this apparently backwards procedure. The arrangement only works on one line. If the orbit is tilted away from the equator, the satellite still takes a day to go round, but it spends half of that day north of the equator and half south. So from the ground it traces a slow figure of 8 in the sky, rather than staying put. It returns to the same place at the same time each day, which is useful, but it does not hang. Only an orbit directly above the equator gives a fixed point. Tilt it, and the fixed point becomes a figure of 8. Real orbits are rarely the neat circles of a diagram. Most are ellipses, with a low point and a high point that have their own names, and the difference between the two can be enormous. A transfer orbit used to carry a satellite from a low parking orbit out to the geostationary belt has its low point a few hundred kilometers up and its high point 35,000 kilometers up, and the spacecraft coasts along it for hours before firing again to circularize at the top. Because the useful line is a single circle around the planet rather than a volume, the space along it is finite, and it is administered. Slots are allocated by international agreement, with satellites kept a fraction of a degree apart, so that ground antennas pointing at one do not also receive the next. A dish bolted to a wall and never moved again is possible only because of this arrangement, and the whole of satellite television rests on it. That two-burn maneuver is the cheapest way to move between two circular orbits, and it was worked out in 1925 by an engineer who never saw a rocket fly. The first burn raises the far side of the orbit. The second, delivered at the top, raises the near side to match. Doing it in one continuous push would cost considerably more fuel. Almost every satellite in a high orbit arrived by this route, and the arithmetic behind it is a century old. At the other end of the range, the low orbits have the opposite character and the opposite uses. 90 minutes to circle the planet means a satellite passes over any given spot briefly and then is gone, and does not come back for another orbit, at best. Nothing can be received from it by a fixed dish, because it will not be there. What it offers instead is closeness. It is 40 to 100 times nearer the ground than the high orbit, which matters enormously for anything involving a camera or a radio delay. Low means close, and close means brief. The delay is the part that is easiest to underestimate. A radio signal traveling to a satellite 35,000 kilometers up and back down again covers 70,000 kilometers at minimum, which takes about a quarter of a second before anything else is added. On a two-way conversation that becomes half a second of silence between speaking and being heard, which is why long-distance telephone calls routed by satellite always had a distinctive pause in them. From low orbit, the same round trip takes a few thousandths of a second. Between the two extremes sit the middle orbits, and they exist for a specific reason rather than as a compromise. At around 20,000 kilometers, a satellite circles twice a day, which means its path repeats over the same ground every day, and a modest number of them can guarantee that several are above the horizon from anywhere at any moment. That is the requirement for navigation, and it is why every satellite navigation system in the world sits at roughly the same height. The middle orbit exists, so several are always in view. None of these heights was chosen by preference. Each one is the answer to a question asked in advance. How often must it come back? How close must it be? How many are needed to cover the planet? And how long may a signal take? The rule converts each answer into an altitude, and the altitude into a speed, and the speed into the amount of fuel required to get there. What looks like a design decision is very often the only arithmetic that fits. The height is an answer, not a preference. Diagrams of the atmosphere usually show it as a band of blue with a clean upper edge, and above that edge a black region marked space. The edge is a convenience of drawing. There is no such line anywhere above the planet. The air simply thins with height, halving in density every few kilometers, and it keeps on halving without ever reaching nothing. Whatever number is chosen as the boundary is a decision taken by people rather than a feature of the sky. There is no edge, only thinning without end. The most widely used figure sits at 100 kilometers, and the reasoning behind it is aeronautical rather than physical. At that height, the air is so thin that a wing would need to travel at orbital speed to generate any lift at all, at which point the wing has become irrelevant and the vehicle is in orbit whether or not it intended to be. The height where flying stops and orbiting begins is a reasonable place to draw a line, and it was drawn there for exactly that reason. The 100-kilometer figure carries the name of the engineer who calculated it, and the calculation is worth restating because it explains why the number is not round by accident. He asked at what altitude an aircraft would need to fly at orbital speed in order for its wings to support it, given how the air thins with height. The answer came out near 83 kilometers. The round figure of 100 was adopted afterward for the convenience of the people who had to write it into agreements. Different authorities use different numbers, and the disagreement is not trivial for the people it concerns. Some national systems place the boundary at 80 kilometers instead, which is why a handful of pilots who flew rocket aircraft in the 1960s are counted as astronauts by one definition and not by another. The physics does not adjudicate. The air at 80 kilometers and at 100 is equally present and equally thin. The boundary is a decision, not a discovery. What matters far more than any boundary is that the thinning never quite stops. At 400 kilometers, where large crewed stations orbit, there are still atoms. Very few of them. The density is something like 100 million times lower than at sea level, which is a better vacuum than most laboratories can produce. But a satellite is moving through that vacuum at 8 kilometers a second, and at that speed, even an almost empty region delivers a steady resistance. The resistance is tiny, and it never stops, which is the combination that matters. A large station loses altitude continuously, on the order of 100 meters a day, and if nothing were done, it would descend to the point where the air becomes thick enough to finish the job. Preventing that requires firing an engine along the direction of travel every few weeks, a maneuver called a reboost, and the fuel for it has to be carried up, along with everything else. A near-perfect vacuum, and it still drags. The thinning has a second consequence that is easy to overlook. Because density falls off so steeply with height, the great majority of the drag a satellite experiences over an entire orbit is delivered in the small part of that orbit closest to the Earth. For an elliptical path, this means the low point is scrubbed hard on every pass, while the high point is barely touched, and the effect is to lower the high point while leaving the low point roughly where it was. An eccentric orbit, therefore, becomes progressively rounder before it decays, which is not what anyone expects. The behavior of a decaying orbit is the opposite of what intuition suggests, and it caused genuine confusion in the early years. Drag removes energy from a satellite, which should slow it down, and it does, but a satellite that has lost energy falls to a lower orbit, and lower orbits are faster. The result is that friction makes a satellite speed up. It circles more quickly, it appears overhead more often, and it does so while steadily losing height. That single counterintuitive fact is what turned satellites into instruments for studying the air. Nobody could sample the upper atmosphere directly. Balloons stop far below and rockets pass through in minutes. But the rate at which an orbit shrinks depends on the density of the air it is plowing through. and the rate at which an orbit shrinks can be measured from the ground with nothing more than a stopwatch and a telescope. The satellite became a probe by the simple act of falling. The satellite measured the air by failing to ignore it. The first results were unwelcome. Early satellites came down noticeably faster than predicted, which meant the air at those heights was thicker than the model said. That was corrected. Then the same satellites began behaving inconsistently from one year to the next, decaying quickly for a period and then more slowly on a rhythm that did not match anything in the atmosphere below. Two satellites at the same height do not decay at the same rate, and the difference is a matter of shape rather than size. What governs the decay is the ratio between the mass of the object and the area it presents to the oncoming air. A dense, compact body pushes through with little effect. A light one with large solar panels is slowed far more for the same mass. This is why a spent rocket stage and a small satellite released at the same altitude on the same day can come down years apart. The rhythm turned out to be the Sunday. Over a cycle of roughly 11 years, the Sun varies in activity, and the ultraviolet and X-ray output rises and falls with it. That radiation is absorbed by the outermost layer of the atmosphere, which heats and expands as a result. When the Sun is active, the upper air swells outward, pushing appreciable density up to heights where there had been almost none, and everything orbiting there begins to decay faster. The upper air breathes with the Sun, and orbits feel it. The magnitude is larger than the word swelling suggests. Between the quietest part of the cycle and the most active, the density at 500 kilometers can change by a factor of 10 or more. A satellite designed to last a decade at solar minimum may last only a few years if it is launched into a rising cycle. Operators therefore plan around a forecast of solar activity, which is a forecast about a star and is accordingly imprecise. There is a further layer of unpredictability on top of the cycle. A single large eruption on the Sun can deposit enough energy into the upper atmosphere within a day or two to raise its density sharply and briefly. Satellites that were where they were expected to be are suddenly slightly lower and slightly ahead, and the catalogues that track thousands of objects go temporarily out of date at exactly the moment when knowing where everything is matters most. One flare, and every catalogue is briefly wrong. All of this makes re-entry prediction unusually poor for something governed by such precise laws. A forecast issued a week before a large object comes down typically carries an uncertainty of a day or more. And since the object circles the planet every 90 minutes, a day of uncertainty means it could land almost anywhere along its ground track. The window narrows only in the final hours, which is why announcements about where something will come down arrive so late and remain so vague. The practical consequence for anyone planning a mission is a hierarchy of certainty that runs opposite to intuition. The orbit itself is predictable to extraordinary precision, because gravity is well understood and does not change. The lifetime of that orbit is not, because it depends on the density of a gas whose temperature is set by a star. An engineer can say exactly where a satellite will be next Tuesday, and cannot say with confidence what year it will come down. That asymmetry sets a natural division in the sky. Below about 600 kilometers, the air cleans up after itself within years or decades, and anything left there will eventually come down whether or not anyone arranges it. Above roughly 1,000 kilometers, the drag becomes so slight that an object will remain for centuries or longer. The same thinning that makes low orbit expensive to maintain is also the only mechanism that empties it, and that will matter a great deal in the final chapter. The air is the only thing that ever tidies up. The first artificial satellite was a polished aluminium sphere 58 centimeters across, weighing about 83 kilograms, carrying 4 whip antennas and almost nothing else. Inside were batteries, a thermometer, a pressure sensor, and 2 radio transmitters. It had no camera, no engine, and no means of pointing itself. It was launched on the 4th of October, 1957, and it did one thing: it beeped. A polished sphere the size of a beach ball. The choice of a beep rather than an instrument was deliberate, and it was shrewd. A tone on a frequency that ordinary shortwave radios could receive meant that anyone, anywhere, could confirm the object existed for themselves. Amateur operators across the world tuned in and heard it, and the fact of it became unarguable within hours. A more sophisticated payload would have been audible only to those with the equipment to decode it. Even the beep carried information. Though the amount was small, the interval between pulses varied with the temperature and pressure inside the sphere, so a listener with a stopwatch was reading telemetry without knowing it. The sphere was pressurized with nitrogen. Had it been punctured by anything, the pressure would have dropped and the pulses would have changed. It was a leak detector that could be heard from the ground. The rhythm of the beeps was the temperature inside. The launch vehicle was not built for this. It was an intercontinental missile, adapted by removing the warhead and fitting a small payload in its place, and that fact was the reason the event mattered so much beyond astronomy. Placing a sphere in orbit and delivering a weapon to the other side of the planet are the same problems solved to the same accuracy. The beeping was harmless. What it demonstrated was not. The polish on the aluminium was also a working choice rather than a decorative one. A reflective surface both keeps sunlight from heating the interior and helps radiate away what heat does accumulate, and the balance between the two determined whether the batteries stayed within their operating range. Thermal control on that first mission was achieved entirely by the finish of the shell and a small fan inside. The batteries lasted 3 weeks, and the beeping stopped. The satellite itself remained in orbit for about 3 months after falling silent, gradually descending until the air brought it down in January of the following year. Its final months were, in the terms of the previous chapter, a slow measurement of atmospheric density made by an object that could no longer report anything. Observers tracked it optically, and its decay curve went into the record. It kept orbiting for 3 months after it went quiet. What followed on the American side was a scramble, and the first attempt failed publicly. A launch vehicle carrying a grapefruit-sized satellite rose about a meter off the pad in December, settled back, and exploded, and the small sphere was thrown clear and landed in the scrub, still transmitting. Newspapers reached for names that mocked it. The satellite it carried is now in a museum, having briefly been in orbit only in the sense that it was above the ground for a second or two. It is worth noting how quickly the situation became ordinary. Within 4 years of the first launch, there were satellites relaying television pictures across the Atlantic, satellites photographing cloud systems from above, and satellites providing position fixes to submarines. The gap between an object whose only function was to prove it could exist and objects doing work that nothing else could do was about 1,000 days. Very few technologies have moved from demonstration to infrastructure at that pace, and none of the people involved expected it to. The successful American launch came on the last day of January 1958, and it carried something that turned out to matter far more than the launch itself. Aboard was a Geiger counter, put there by James Van Allen to measure cosmic rays, which were expected to produce a modest and steady count. It was a small instrument on a small satellite, and nobody anticipated much from it. A Geiger counter expected to record almost nothing. The counter behaved strangely. At low altitudes, it reported the expected modest rate. Higher up, it reported nothing at all, a flat zero, as though it had failed. The pattern repeated on every orbit, and it correlated with height rather than with anything else, which is not how instruments usually break. A broken counter reads 0 everywhere or nonsense everywhere. This one was reading sensibly in one place and 0 in another. A graduate student working on the data suggested the explanation, and it was the right one. The counter was not failing, it was saturating. The radiation at those heights was so intense that the instrument could not recover between counts and was reading a continuous stream as no counts at all. The 0 was not an absence of radiation but an overwhelming excess of it, and the region above the satellite was full of trapped charged particles nobody had known were there. The 0 did not mean nothing, it meant too much. Tracking these first objects was a distributed effort involving a great many ordinary people. A volunteer program equipped amateur observers with simple wide-field telescopes and trained them to time a satellite crossing a north-south line, reporting the moment by telegram. Hundreds of teams around the world contributed, and for the first years their timings were a substantial part of how orbits were determined at all. The professional networks that replaced them took most of a decade to build. What had been found are the belts of particles held by the Earth's magnetic field, arranged in 2 donut-shaped regions around the planet. Protons and electrons arriving from the Sun and from beyond are captured by the field and bounce back and forth between the magnetic poles, sometimes for years. It is the largest structure surrounding the Earth, and it had been entirely invisible from the ground, because the particles it holds never reach the ground. None of this happened in a vacuum of intent. Both launches fell inside a coordinated scientific program agreed years earlier, in which dozens of nations undertook to study the Earth simultaneously with every instrument available. Placing a satellite had been announced as a goal of that program by both parties well in advance. The competition was real, but the schedule and much of the scientific justification came from an agreement to cooperate. The discovery has shaped every mission since, and it is one of the reasons the useful orbits described in the previous chapter are arranged as they are. The belts are a hostile environment for electronics. A satellite that lingers in them accumulates damage that shortens its life. Spacecraft are therefore placed below the inner belt or beyond the outer one, and anything that must cross them is designed to do so quickly and with shielding. The largest thing around the Earth was invisible. There is a pattern in these first years that recurs throughout the subject. The instruments that were expected to be decisive returned modest results, and the discoveries came from things nobody had gone looking for. A radio beacon meant to prove a launch had happened became a thermometer. A satellite meant to establish a presence became a measurement of the upper atmosphere by falling out of it. A counter meant to tally cosmic rays found a structure the size of the planet by reading 0. It is worth adding what these objects were not. None of them was useful in the way satellites are useful now. They carried no communications, took no pictures, guided nothing, and served no customer. Their entire contribution was to demonstrate that the arithmetic worked in practice and that an object could be placed and kept where the calculations said it would be. Everything described in the remaining chapters rests on that demonstration and on very little else. They proved the arithmetic worked, and nothing more. A satellite in orbit is an unusually honest instrument for measuring the planet it circles, and the reason is that it touches nothing. A survey carried out on the ground has to contend with mountains, oceans, borders, and the difficulty of comparing a measurement made in one country with one made in another. A satellite passes over all of it at the same height, on a path decided by gravity alone, and every deviation from that path is information. It measures the Earth by touching none of it. The starting assumption was that the Earth is a sphere flattened slightly at the poles, which had been established well before anything flew. The flattening comes from rotation. The ground at the equator is moving fastest and bulges outward, so the distance from the center to the equator exceeds the distance from the center to the poles by about 21 kilometers. That much was known and agreed. What satellites added was that the flattened sphere is not the whole story. The tracks of the earliest American satellites showed small, regular wobbles that a smooth, flattened shape could not produce. Analyzing them revealed that the planet is very slightly asymmetric between north and south. The South Pole sits a little closer to the center than the North Pole does, and the mid-latitudes are correspondingly displaced. The press of the day called it pear-shaped, which overstates it considerably. There is a word for the shape these measurements converge on, and it is not sphere or ellipsoid. The geoid is the surface along which gravity has the same strength everywhere, the shape the oceans would take if they were free to settle without tides, winds, or currents. It is lumpy, by tens of meters in places, and it is what sea level actually means. Every altitude printed on a map is measured from it rather than from any geometric figure. The South Pole sits closer to the center than the North. The largest departure is in the Indian Ocean, where the geoid sits about 100 meters below the smooth ellipsoid over an area larger than a continent. Sea level there is genuinely lower than the geometry would predict, and the cause lies hundreds of kilometers down in the mantle rather than anywhere on the surface. A satellite passing above that region is pulled fractionally less, and it was satellites that first mapped the depression properly. The scale deserves stating plainly, because the phrase pear-shaped has done a great deal of harm to people's mental picture. The asymmetry amounts to something like 17 meters on a body 6,000 kilometers in radius. If the Earth were shrunk to the size of a billiard ball, it would be smoother than the ball, and the pear shape would be far too small to feel. The measurement is remarkable not because the effect is large, but because it was detected at all, from the wobble of a metal object a few hundred kilometers up. Once the principle was established, the method could be pushed much further. The path of a satellite responds to every unevenness in the distribution of mass beneath it, not merely to the overall shape. A mountain range represents extra material and pulls a passing satellite very slightly toward it. A deep basin represents a deficit and pulls slightly less. Tracking a satellite accurately enough therefore maps the interior of the planet as well as its surface. Every mountain tugs on everything passing above it. The most elegant version of this idea flew as a pair rather than a single spacecraft, and its arrangement is worth describing carefully. Two identical satellites follow one another in the same orbit, separated by a couple of hundred kilometers. with a microwave link continuously measuring the distance between them. That distance is known to within a fraction of the width of a human hair. The precision now available makes it possible to watch the ground itself move. Continuous measurements from satellites show continents drifting at a few centimeters a year, the rate at which fingernails grow, and they show it directly, rather than by inference from magnetic stripes on the sea floor. They also show the daily flexing of the whole solid Earth under the tidal pull of the Moon, which raises the ground beneath any given city by a few tens of centimeters twice a day. Nobody feels it, because everything nearby rises at the same time. When the leading satellite passes over a region of greater mass, it is pulled forward slightly, and the gap widens. As the trailing satellite reaches the same region, it is pulled forward in turn, and the gap closes again. The pattern of widening and closing, recorded all the way around the orbit and over many orbits, reconstructs the gravity field of the entire planet. Neither satellite measures gravity directly. The measurement lives in the distance between them. Neither one measures gravity, only the gap between them. The result that made this famous was not a map, but a film. Because the pair could produce a new gravity field every month, and because gravity responds to mass, comparing one month with the next shows where mass has moved. Water is the mass that moves most. Ice sheets losing volume, aquifers being drained, river basins flooding and drying, all of it shows up as a change in the local pull, and all of it can be weighed from orbit. It is worth appreciating what this replaced. Before it, estimating how much ice a region had lost meant surveying its surface height, which requires assumptions about the density of what is there, or counting the water arriving at the coast, which requires assumptions about everything in between. The gravity method skips the assumptions entirely. It does not measure area or thickness, it measures mass, and mass is the quantity that actually matters. A second technique deserves mention because it is the simplest idea in the chapter. Certain satellites carry nothing but arrays of corner reflectors, which return any light striking them straight back to its source. A ground station fires a laser pulse, waits, and times the return, which gives the distance to within a few millimeters. The satellites themselves have no power, no electronics, and no lifetime limit. Some launched in the 1970s are still in routine use. It does not measure the ice, it weighs it. The same sensitivity produces a complication that had to be untangled before the results could be trusted. The crust of the Earth is still rising in regions that were buried under ice 10,000 years ago, as described in more detail in other subjects, and that rising rock is also a movement of mass. It shows up in the gravity data alongside the melting ice, in the same places and with the opposite sign. Separating the two required an independent model of the rebound, and the accuracy of the final numbers depends on it. There is a related measurement that is easier to describe and just as unexpected. Satellites carrying radar altimeters bounce a pulse off the sea surface and time its return, which gives the height of the water beneath them to within a few centimeters. Repeated over decades and over the whole ocean, this produces a record of sea level that no network of coastal tide gauges could match, because tide gauges sit on coasts that are themselves moving up and down. A tide gauge moves with its coast, an orbit does not. Taken together, these methods invert the usual relationship between the observer and the observed. The satellite was placed in orbit by applying what was known about the Earth's gravity, and it then improved that knowledge by the manner of its own falling. Each better gravity model allows the next satellite to be placed and tracked more precisely, which produces a better model again. The instrument and the thing it measures refine one another, and neither was ever touched. The falling object improved the law that placed it. One last thing, quietly. If you are still here, a like and a subscription cost you nothing, and they let this channel keep making long, calm videos with no adverts. Now, back to it. On a clear evening, 20 minutes or so after sunset, it is possible to stand outside and watch satellites cross the sky. They look like stars that have decided to travel, moving steadily, taking 3 or 4 minutes to go from one horizon to the other, never blinking. There is no equipment involved. The largest of them are among the brighter objects in the night sky, and on a good pass they are impossible to miss once you know what you are looking at. A star that travels and never blinks. The light is entirely borrowed. Nothing up there is glowing on its own account. What reaches the eye is sunlight that has struck an aluminium panel or a solar array and bounced downward. This is the same arrangement that makes the moon and the planets visible, applied to objects a few meters across instead of a few thousand kilometers. What makes it work at all is that the reflecting surfaces are engineered ones, flat and clean, and they reflect far better than rock. The timing is the part that seems arbitrary and is not. Satellites are visible in a window after sunset and before sunrise, and only then, because 2 conditions must hold at once. The observer must be in darkness, so that the sky is black enough for a faint moving point to stand out, and the satellite must still be in sunlight, several hundred kilometers up, where the sun has not yet set because the horizon is further away. Dark below, still daylight, 400 kilometers up. The Earth's shadow is a cone reaching out into space behind the planet, and the height at which that cone begins over any given place changes through the night. Shortly after sunset, the shadow is low, and satellites well above it stay lit. As the night deepens, the shadow rises, and by the middle of the night, it covers the altitudes where most satellites orbit, and they all go dark. Toward dawn, the process reverses. The observing window is the gap between the ground going dark and the orbit going dark. Knowing where to look is mostly a matter of knowing which direction things travel. Satellites in the common low orbits move roughly from west to east, because launching in the direction the Earth already turns is cheaper, and almost everything is launched that way. Those in the imaging orbits described later travel nearly north to south instead. A point of light crossing from west to east in the twilight is far more likely to be a satellite than an aircraft, which will also be blinking. The most striking thing to watch for is not the arrival but the departure. A satellite crossing the sky may fly into the Earth's shadow while still well above the horizon, and when it does not set. It fades, over perhaps 10 or 15 seconds, going from clearly visible to orange to nothing at all while continuing along its path. What is being watched is a sunset, observed from below, happening to an object 400 kilometers up. It does not set, it fades in the middle of the sky. How bright any particular object appears depends on 3 things that have nothing to do with each other. Its size, obviously, since a larger reflector returns more light. Its distance, since a satellite directly overhead is far closer than the same satellite low on the horizon. And the angle, which is the one that dominates. A flat panel returns light strongly in one direction and weakly in all others. So brightness depends on whether the geometry happens to line up. There is a particular kind of pass that is worth waiting for, and it happens only near the boundary of the visibility window. If a satellite enters the Earth's shadow while still fairly high in the sky, the last light reaching it has grazed the edge of the planet and passed through the whole depth of the atmosphere, exactly as the light of a sunset does. It is reddened by the same process and for the same reason. For a few seconds before it disappears, the moving point turns distinctly orange. When the geometry does line up exactly, the effect is dramatic and brief. One early generation of communication satellites carried 3 flat antenna panels with a mirror finish, angled outward, and when one of those panels caught the sun and directed the reflection at an observer, the satellite brightened enormously for a few seconds before fading again. At its peak, such a flare could outshine every star in the sky and be visible in daylight. A mirror the size of a door, catching the sun. Because those flares depended purely on geometry, they were entirely predictable. Software could tell an observer the exact second and the exact patch of ground a few kilometers wide from which a given flare would be seen. People drove to those patches and stood in fields at the appointed minute, and the flare arrived on schedule. That generation of satellites has since been retired and the flares have stopped, which is a small and specific loss to the night sky. The brightest object regularly visible is the Large Crude Station, and it is bright for a straightforward reason. It is enormous by the standards of anything else up there, with solar arrays spanning about the width of a football pitch. On a high overhead pass, it outshines every star and every planet, and it takes about 6 minutes to cross from horizon to horizon. It is also the only one where the light is arriving from a structure with people inside it. The population overhead has changed character in recent years, and the change is visible to anyone who looks. Satellites launched in large groups are released together and drift apart slowly. So, for the first weeks after a launch, they cross the sky as a chain of evenly spaced lights, following the same path one after another. It looks deliberate and it looks nothing like anything natural, which has caused a good deal of confusion among people who happen to look up at the wrong moment. There is a second way to detect satellites that requires no darkness and no clear sky. Many of them transmit on frequencies an ordinary receiver can pick up, and the pitch of the signal shifts as the satellite approaches and recedes, exactly as the pitch of a passing siren does. Timing that shift against a clock is how the very first satellite navigation system worked. A ship listened to the tone, measured how it slid, and derived its own position from the shape of the curve. A chain of lights, evenly spaced, all on one path. For astronomy, the same brightness is a difficulty rather than a spectacle. A long exposure of a patch of sky now frequently contains bright straight lines where a satellite crossed during the exposure, and the affected pixels are unusable. The problem is worst in exactly the hours after dusk and before dawn, which are also the hours when telescopes observe the parts of the sky closest to the sun, where certain objects can only be found. Some mitigation is possible and has been attempted. Darkening the surfaces reduces reflection, though it also makes the satellite run hotter, since a black object absorbs the sunlight it no longer reflects. Adjusting the orientation so that the flat panels face away from the ground during the twilight hours helps as well. Both approaches trade a little performance for a little darkness, and neither removes the streaks entirely. Painting it dark makes it hotter, not simpler. It is worth remembering, standing outside and watching one go over, how little is actually being seen. The object is a few meters across. further away than most people have ever traveled, moving at 8 kilometers a second, and it is visible only because a flat piece of metal on it happens to be angled correctly toward a star that set 20 minutes ago. Everything about the sighting is a coincidence of geometry, and it repeats, reliably, several times a night. Most orbits in use today were not discovered. They were specified in advance by someone who worked out what a particular job required and then asked what path would deliver it. The paths came first and the hardware followed, sometimes by decades. This is unusual in engineering, where the tool is normally built and the use is found afterward, and it happens here because the arithmetic of orbits is complete enough to design in. The path was specified before anything could fly. The clearest case was published in 1945 in a technical magazine by a radar officer who would later become a novelist. Arthur Clarke set out the consequences of the height at which an orbit takes exactly 1 day, and observed that a station placed there would appear fixed above one point on the equator. He then made the argument that mattered. 3 such stations, spaced evenly around the equator, would between them have line of sight to almost the entire inhabited surface of the planet. That paper appeared 12 years before anything at all was placed in orbit, and about 20 years before anything was placed in that particular orbit. The physics required no new discovery. Kepler's rule gives the height directly, and had done so for 3 centuries. What was new was noticing that the height had a use. The belt is now named after him, and it carries several hundred spacecraft. 3 stations would cover the inhabited world. The second designed orbit solves an entirely different problem, and its solution comes from an imperfection rather than from the ideal case. A satellite in a tilted orbit does not keep the same orientation relative to the Sun because the Earth is not a perfect sphere. The equatorial bulge tugs on the orbit and causes the whole path to rotate slowly around the planet's axis. For most missions, this drift is a nuisance to be corrected. For imaging satellites, it is the entire point. If the tilt is chosen correctly, slightly more than 90 degrees so that the satellite travels almost over the poles, and very slightly backwards, the drift comes out at exactly 1 full turn per year. The orbit then keeps pace with the Earth's journey around the Sun, and the satellite crosses the equator at the same local solar time on every single pass, year after year. A defect in the Earth turned into a clock. The value of that is not obvious until you consider what it means to compare 2 photographs. An image of a forest taken at 9 in the morning and another taken at 3 in the afternoon differ in the direction and length of every shadow, in the color temperature of the light, and in the apparent brightness of every slope. Any change between them is buried under changes in illumination. Fix the local time of the pass, and the lighting becomes a constant, and what remains in the difference is the forest. Almost every long-running record of the surface of the Earth depends on this arrangement. Deforestation, ice extent, crop health, urban growth, and coastline change are all measured by comparing images separated by years, and none of those comparisons would be reliable without the guarantee that the Sun was in the same place each time. The orbit was designed to make the light boring, and boring light is what makes measurement possible. Holding a slot in the geostationary belt is not passive, and the fuel it consumes is the main thing that limits the working life of the satellites there. The pull of the Moon and the Sun steadily tilts the orbit away from the equator, and left alone, a satellite would drift into the figure of 8 described earlier within a few years. Correcting that tilt requires firing thrusters sideways several times a year, and it accounts for most of the propellant a communications satellite ever uses. The orbit exists to make the light boring. One further design exists mainly as a demonstration of how far the reasoning can be pushed. A satellite can be placed not in orbit around the Earth at all, but at one of a handful of points where the pull of the Earth and the Sun combine with the motion of both to hold a spacecraft in a fixed relationship to the pair. A telescope stationed at the point directly away from the Sun keeps the Earth, the Sun, and the Moon permanently behind it, which is the only way to keep an instrument permanently cold and permanently shaded without carrying a coolant supply. The belt is also not perfectly level in the sense that matters. Because the Earth is slightly out of roundabout its equator, there are 2 longitudes where a satellite naturally settles and 2 where it naturally slides away, and a spacecraft left unattended will drift toward the nearest stable point and oscillate about it for centuries. Those 2 stable longitudes are consequently crowded with derelict hardware that nobody moved before it stopped responding. A third design answers a problem that the geostationary belt cannot solve at all. A satellite above the equator sits low on the horizon when seen from high latitudes, and from far enough north it never rises above the horizon at all. So the countries that most needed reliable communication over a vast northern territory could not use the belt. The answer was to abandon the circle entirely. The orbit adopted is strongly elliptical and steeply tilted, with its low point over the southern hemisphere and its high point over the north. Because a body in an ellipse moves quickly when close and slowly when distant, such a satellite races through the southern half of its path in under an hour and then loiters over the northern sky for something like 8 hours out of a 12-hour circuit. 3 satellites in that arrangement, spaced in time, keep one of them permanently high over the north. It loiters where it is needed and races where it is not. It is worth adding what the 1945 paper got wrong, since it was not a prophecy. Its author assumed the stations would have to be inhabited, because he could not imagine electronics of the day running unattended for years, and he sketched crews rotating on and off them. The satellites that occupy the belt today are uncrewed and are visited by nobody. The orbit was right, the coverage argument was right, and the thing he thought hardest to arrange turned out to be unnecessary. The 4th design is the one most people carry in a pocket, and its requirement is different again. Navigation does not need a satellite to stay above a point, nor to pass at a fixed hour. It needs several satellites to be simultaneously visible from anywhere on Earth at any instant, because a position is calculated from the distance to 4 of them at once. The design problem is coverage rather than persistence. The solution is a set of interlocking rings. Around 20,000 kilometers up, where a circuit takes about 12 hours, satellites are distributed across 6 tilted orbital planes, with several in each plane. The geometry is arranged so that from any point on the surface, at any moment, at least 4, and usually more, are above the horizon and well separated in the sky. Separation matters as much as number, because 4 satellites clustered together give a poor fix. 4 in view is not enough. They must be spread apart. There is a detail in how those systems work that belongs in this chapter because it connects back to the beginning of the video. The position calculation depends on timing radio signals to within billionths of a second, and at that precision, the clocks aboard the satellites do not tick at the same rate as clocks on the ground. They run fast because they are higher in the Earth's gravity, and slow because they are moving quickly, and the two effects do not cancel. The net result is that a navigation satellite's clock gains about 38 millionths of a second every day relative to the ground. Left uncorrected, that would introduce a positional error growing by roughly 10 kilometers per day, which would make the entire system useless within hours. The correction is built into the clocks before launch. They are deliberately set to run slow, so that once in orbit, they run right. The clocks are set wrong on purpose, so they run right. 4 requirements, 4 orbits, and not one of them chosen for convenience. Stay above a point, and the height is fixed at 35,800 kilometers over the equator. Keep the light constant, and the tilt is fixed near 98 degrees. Serve the far north, and the circle must become an ellipse. Cover everywhere at once, and the answer is 6 interlocking planes halfway out. In every case, the job was stated first, and the path fell out of the arithmetic. Every orbit low enough to be useful is also low enough to be temporary. The thin air described earlier removes a little energy on every circuit. The path shrinks, the lower path passes through slightly thicker air, and the process accelerates by feeding itself. For most of a satellite's life, the effect is barely measurable. At the end, it becomes rapid, and the last stage of a decay that took 15 years occupies a single afternoon. 15 years of decay, and then one afternoon. The shape of that ending is worth describing because it is counterintuitive in the same way the drag itself was. A satellite does not tip over and dive. It spirals, staying very nearly horizontal, going slightly faster on each circuit as it drops. The final descent through the dense air happens at a shallow angle, which is why re-entry heating lasts minutes rather than seconds, and why the debris field of anything that survives is spread over hundreds of kilometers rather than concentrated at a point. The heat itself is commonly misattributed. It is generally assumed that a returning object burns because of friction against the air, and friction plays only a small part. What actually happens is compression. The object is moving so much faster than sound that the air cannot move out of the way and is instead squeezed violently in front of it, and squeezing a gas heats it. The glow surrounds a returning spacecraft at a small distance rather than touching it, which is precisely why a heat shield works at all. It is not friction, it is air with nowhere to go. Most of what comes down does not reach the ground. A typical satellite is a lightweight structure of aluminium and composite panels, and it comes apart at high altitude and vaporizes. But certain components routinely survive, and they are predictable. Tanks made of titanium or stainless steel, which have high melting points and are built to be strong. Reaction wheels with dense metal rims, and optical elements made of glass ceramics, chosen for surviving temperature extremes. Because the surviving pieces are known in advance, they are designed for. The discipline of design for demise arranges that tanks are placed where they will be exposed early and break up rather than being protected inside a structure, and it favors materials that fail at lower temperatures where a choice exists. A satellite is therefore engineered twice, once to work and once to disappear properly. It is engineered to work, then engineered to vanish. There is a category of object that complicates every calculation in this chapter, and it is the one nobody put there deliberately. Rocket upper stages reach orbit alongside their payloads and stay there, and they are typically far larger than the satellites they delivered. Several thousand of them are up there now, most with no means of maneuvering, some still holding residual propellant. They are the heaviest single class of derelict object in low orbit, and the most consequential if one is struck. For anything large enough that pieces will certainly reach the sea or the ground, the re-entry is aimed rather than awaited. There is a stretch of the South Pacific, centered roughly halfway between New Zealand and South America, which is the furthest point on Earth from any land. It is the standard destination for controlled re-entries, and the floor there holds the remains of several hundred spacecraft, including an entire space station brought down deliberately in 2001. The furthest place from land, used as a cemetery. High orbits present the opposite problem, and it does not have the same solution. A satellite in the geostationary belt is far too high for the air to reach, and bringing it all the way down would require nearly as much fuel as putting it there in the first place. Nothing at that altitude will ever come down on its own, on any timescale that means anything. Tracking what is up there is harder than the numbers suggest. Radar can find objects down to about 10 centimeters in low orbit, and everything smaller is inferred statistically rather than catalogued, which means the population most likely to cause damage is precisely the population nobody can point at. A fragment too small to track cannot be avoided, only survived, and survival is a matter of shielding a few critical components and accepting that the rest of the spacecraft is exposed. Most satellites have already been struck by something. Almost none of them noticed. The convention adopted instead is to move retired spacecraft up rather than down. A few hundred kilometers above the working belt is a region designated for disposal, and a satellite reaching the end of its life is expected to reserve enough fuel for that final climb. It is a modest maneuver and a permanent one. Nothing placed there will return. The arrangement works only because everyone follows it, and compliance has historically been imperfect. At that height, retirement means climbing away. Reserving that fuel is a real cost, and it is paid by the operator against a benefit that accrues to everyone. The propellant set aside for the disposal climb is propellant not spent on keeping the satellite in its slot, and it therefore shortens the revenue-earning life of the spacecraft by several months. The incentive to skip it is obvious, which is why the rule exists as an agreement rather than a preference. What accumulates when disposal does not happen is the subject that now governs the whole field. There are tens of thousands of tracked objects in orbit larger than 10 centimeters, and many millions of fragments too small to track. At orbital speeds, a fragment a centimeter across carries the energy of a small car at motorway speed, and a paint fleck can pit a window. Nothing up there is slow enough for size to be reassuring. A centimeter of debris hits like a car on a motorway. Actually, removing debris has been attempted only at demonstration scale, and the difficulty is not the catching. A derelict satellite is usually tumbling, often slowly but about an unpredictable axis, and anything approaching it must match that tumble before making contact, or it will simply create more fragments. Nets, harpoons, and magnetic capture have each been flown against cooperative test targets. None has yet been used on a real derelict. The concern is not primarily that debris might strike a working satellite, though it does. It is that debris makes more debris. A collision between two large objects produces thousands of fragments, each of which is itself capable of causing a collision, and above a certain density, the process sustains itself without any further launches. The scenario was described in 1978, and it carries the name of the man who set it out. The economics are the harder half of the problem. Each removal mission costs roughly what a small satellite costs to launch, and it removes exactly one object out of tens of thousands. There is no operator with an incentive to pay for it, since the benefit is shared by everyone who uses the orbit and by nobody in particular. It is the same structure as the disposal fuel described earlier, at a much larger scale and without an agreement in place. Two events have demonstrated the mechanism at full scale. In 2007, a satellite was destroyed deliberately as a weapons test, producing more than 3,000 tracked fragments, many in orbits that will persist for decades. 2 years later, two satellites collided by accident, one working and one long dead, adding a comparable quantity. Between them, those two events account for a substantial share of everything now catalogued at that altitude. Two events and a third of the catalogue. The remedies under discussion are unglamorous and mostly consist of restraint. Rocket stages are vented of leftover propellant so that they cannot explode years later, which was a significant source of fragments. Satellites are required to remove themselves within a set period after their mission ends, and the period has been shortened. Collision warnings are issued and working spacecraft maneuver to avoid each other several times a year. It is a fitting place to end because it returns to where the video began. An orbit is a fall that keeps missing, and nothing that has been launched has ever stopped falling. Everything above us is either on its way down slowly, or holding its height by spending fuel, or waiting in a higher parking place because coming down was too expensive. The arithmetic that put each of them there also decides, without any further decision, how each one ends. Nothing ever stopped falling. It only takes longer. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.